This one's probably going to be our shortest video to understand the chemistry of carbonic anhydrase. So we've seen carbonic anhydrase a few times now, right? We saw it in our aspirin overdose case study because we understood how our respiration rate can affect the carbon dioxide that gets into our blood and ultimately our blood pH. We saw it in our hemoglobin highway, so we understood how it kind of played into the role of hemoglobin and oxygen delivery in the body. So now we're finally going to just take a deep dive into how this enzyme actually does its chemistry. So as we're going to have with all of our videos here on enzymes that we're studying, we'll first start by a little bit of a discussion as to what this enzyme is and where we find it, and then we'll spend some time looking at the uncatalyzed reaction, and then we'll map that on to what we see in the enzyme active site. Okay, carbonic anhydrase, right? Its purpose is the reversible reaction that interconverts gaseous carbon dioxide with soluble bicarbonate. So we'll write that down on the next slide. But it's H2O plus CO2 makes H2CO3, which as a weak acid dissociates into bicarbonate ions and protons. Okay. Structurally, some important pieces that we're going to see here is there's an essential hydrated zinc ion that's coordinated in the enzyme active site by 3 histidine residues. So I'm just going to zoom in here so we can sort of see that. Okay, that little sphere right there, that's our zinc ion that we've got coordinated there. When we kind of zoom into the enzyme active site here, we can see that there's that zinc and we've got 3 histidine residues that are coordinating it. So those histidine residues are not doing what we've seen in the past, like with RNase A. They're not doing acid-base chemistry, but they're actually being used to coordinate and position an essential zinc ion here. So just a little comment on why we see or some enzymes need metals. Sometimes there's actually, and we call those enzymes metalloenzymes. Sometimes there's actually redox chemistry that's going on. Remember we talked about the fact that amino acid residues really don't have the functionality to participate in doing redox chemistry, but certain metals do. Iron can go between ferric and ferrous states, right? We can have copper going between copper 2+ and copper 1+. Manganese and cobalt also have the potential for redox activity. There's also non-redox chemistry, so we can have highly charged metals like magnesium and zinc, and we're going to see an example with zinc here, perform some other chemistries, and sometimes you just have structural roles. Remember, these are just giant pieces of bubble gum when we bring all of these amino acid residues together, and sometimes you need to put a positive charge someplace to help stabilize or lock things in. So sometimes they just play a structural role. Sometimes they might be responsible for binding and orienting things that are charged, specifically anionic substrates. We're going to have these metals that are charged, maybe provide a nice cationic pocket that's going to be a docking space for an anionic substrate. Additionally, remember, charge that gets built up as we have reactants be converted to products or substrates converted to products, that's unfavorable. So anything that the enzyme active site can do to stabilize that negative charge buildup is going to help that chemistry proceed. And stabilizing that charge, particularly if it's a negative charge, can be done with metal ions. Okay. So let's take a second. For this one, I'm actually going to write this stuff out because it's a pretty simple mechanism, so we don't need to kind of write it out beforehand. Let's again remind ourselves the chemistry that we have with carbonic anhydrase. Okay, it's the assembly of water and carbon dioxide to make carbonic acid. And then because carbonic acid is a weak base, we've got a dissociation. Sorry, it's a weak acid. We've got a dissociation into bicarbonate ions and protons, right? That pKa is 6.35. So an important thing that we've had to learn from before. Running through kind of what we need to see mechanistically. So again, we're going to have carbon dioxide here. This is going to be our electrophile. We're going to have water here as our nucleophile. So if we think about mechanistically, it's pretty straightforward. Nucleophilic attack, okay? We're going to have to move those electrons. Let me finish making my Lewis structure, putting all my lone pairs in, okay? We're going to end up, I'm going to kind of keep things in the same sort of position so we can see where atoms went, okay? Now what we need to have happen to sort of finish out this chemistry is we can have a base that can deprotonate and get rid of that positive charge. Highlighting, if you wanted, you could think about that deprotonation step happening first, actually making that water a better nucleophile. And whether or not you have sort of this last piece happen is less important because of the pKa of carboxylic of the carbonic acid. Sorry, I could not think about that for a second. Is we could have protonation here, okay, to generate this in its fully protonated form. So we're going to draw it like this. But again, if you left it as deprotonated on top, because that's what the physiological pH would say, that's fine too. But highlighting, if you wanted, you could actually have this proton get involved earlier, maybe thinking about sort of protonating one of those oxygens, which would help make that carbon of that carbon dioxide much more electrophilic. But regardless, what we can see here is we are going to have the need for water to be a nucleophile and interact with carbon dioxide as an electrophile. So how does zinc actually get involved with this chemistry? Okay, so what we're going to see here, and this is a general theme for any metals that are bound to water. So we call this coordination. Okay, so we can have water that is coordinated. So this is coordination. Let me just highlight this right here so we can sort of see we're talking about coordination there. When we have that coordination, what happens is an inductive electron withdrawal. And so we're going to have the pulling of an electron blanket, if you will, towards that positively charged metal. So we're going to have what we call inductive electron withdrawal. So this is like an inductive electron withdrawing group. So highlighting what's happening here is we're pulling electron density that way. Okay. What this does is this is going to decrease the pKa of the water that is bound there. So the net effect is we're going to have this metal, okay, which is going to be coordinated now to a hydroxide, okay? Water normally has a pKa of 14. So when we decrease that, we're actually going to make water more acidic, and we're going to have that proton then kind of is just gone somewhere in solution. And so the net effect is that we've got this water that's now a hydroxide that's bound in the enzyme active site. So we're going to have hydroxide in the active site. And this is important, without changing pH. So the net effect here is that we're able to increase the effective concentration of hydroxide without changing the pH. So that's going to allow us to have a higher concentration of a more effective nucleophile without changing pH. So that's kind of a neat thing that metals are able to do when they bind water and when they're in an enzyme active site. Okay. So let's take a look at what we have here. So here's the enzyme active site. There's not too much that we're going to do here. We don't have sort of those little eggshells that we have that sort of describe what's going on, because this is a pretty straightforward sort of system here. This is not one that you're likely to see me asking you detailing questions on a quiz or an exam. But zooming into what we have here, okay, so again, here's that zinc, and there's that water that's bound to zinc, and we can see it coordinated by these histidine residues that's here. Note here too, we've talked about this. When we see these numbers represent where these amino acids are in primary sequence space. So we can see that these two are actually close to one another. They just are one amino acid residue apart. That this guy is way far down the road. But when this enzyme folds into its active, three-dimensional structure, it brings these residues together. So let's look at this here. Now remember, we talk about that histidine ring is very similar to the organic molecule imidazole. So that's why this is called IM. These are really these histidine rings that are bound to zinc, highlighting here that zinc, in pulling that electron density away, allows for water to be more effectively deprotonated. So we effectively have a hydroxide ion bound to that zinc rather than water. But now we're going to see the same chemistry that we saw in our uncatalyzed reaction. Nucleophilic attack on our carbon of our carbon dioxide. And again, we generate, at this point, we've done chemistry. Let's go ahead and map that on here, right? We've done chemistry. So we've done chemistry. Chemistry on the substrate. We actually made carbonic acid, okay? But we haven't used water, and we haven't returned the enzyme to its active state, because if this guy leaves, zinc doesn't have anything attached. So now we're going to have water come in, so it's going to use all of our reagents, and then we regenerate our enzyme active site by allowing that water to bind to zinc, and then it's going to have its proton be removed because of that lowered pKa value. Okay, so again, we can see the details of this enzyme speak here. Histidine 94, 96, and 119 help to coordinate a zinc atom, acting via electrostatic catalysis to decrease the pKa of the metal-bound water, increasing its nucleophilicity for attack on the electrophilic carbon of carbon dioxide. Departure of that bicarbonate allows water to diffuse into the enzyme active site, bind to the zinc atom, and regenerate the enzyme active site. So pretty straightforward and fairly simple for the chemistry that happens then with carbonic anhydrase.